Hi, everyone. My name is Seth Muthukaruppan. I'm a consultant at Instacluster, which is now part of Spot by NetApp. My area of expertise is search technologies such as OpenSearch, Elasticsearch, and Solr. Today, I'm going to be covering OpenSearch, which is a new entrant in the search engine space. And I'll be covering the architectural aspects of OpenSearch. So let's get started. So in this presentation, I will provide a brief overview of OpenSearch, some of the common use cases. I'll talk about Apache Lucene search library and how OpenSearch uses Lucene and clustering to provide a scalable search solution. And I will touch upon how data is organized within OpenSearch, how document indexing works, and how the documents are searched. And I will also briefly cover aggregations, which are helpful for doing data analytics. Right. So with that, let's get started. OpenSearch is a search and analytics engine built with the Apache Lucene search library. And although it is a new entrant to the search engine space, if you come from an Elastic world, then you will find a lot in common. The reason being that OpenSearch is derived from Elasticsearch. In particular, it is derived from the open source version of Elasticsearch version 7.10.2. And the OpenSearch dashboard, which is the Kibana equivalent, is derived from Elasticsearch Kibana version 7.10.2, and again, the open source version of it. The difference here is that OpenSearch is 100% open source, and it is 2.0 license, which means that it can be viewed, modified, and used and redistributed for free. It is community driven and maintained by the open source community with backing from industry leaders such as Amazon and Red Hat. So to recap, if you don't want to be locked into a particular vendor or a product and don't want to pay expensive licensing fees, then OpenSearch will be a great choice because it is 100% open source. It's 2.0 licensed. And it is enterprise grade. It has the core set of features similar to Elasticsearch. And it is community driven. There is a very active community behind OpenSearch. And a lot of features are being developed as we speak. So let's look at some of the core features of OpenSearch. And then some of these topics we'll look at in detail later. But let's start with scalability. OpenSearch is built with a distributed architecture. So that means that it is horizontally scalable. So you can add thousands of nodes, and the cluster can handle petabytes of data. And OpenSearch is also highly available, again, because of the distributed nature of the cluster. You can do data replications across nodes, across availability zones. Not only that, even across clusters, in different regions. And you can also make use of the snapshots to take a backup of your data, which then can be used to restore data in the case of a data loss. And talking about search, OpenSearch is built for search, and that's where it really shines. It can provide extremely fast search results, and it comes built with a lot of search text search capabilities such as fuzzy match, auto completion, and all that. And it also has a built-in set of analyzers and tokenizers that come in handy when you have different set of documents that you want to ingest into OpenSearch. And on the analytics side, OpenSearch has built-in capabilities for faceting, aggregations, doing reporting, and also for performing anomaly detection. And OpenSearch is not a standalone product. There's a larger ecosystem around OpenSearch, particularly the OpenSearch dashboard, which is the Kibana equivalent, which you use to interact with OpenSearch to configure it, to set up your users or set up your dashboards and visualizations. And to get the data into OpenSearch, you can use Logstash, Beats, or some of the REST clients. Many of these were developed for Elasticsearch, but a lot of them will work with OpenSearch as well. And there have been folks of these tools and clients for OpenSearch specific use cases as well. And again, if you look at the building blocks, you have OpenSearch, which is the main search engine that is based on Elasticsearch OSS 7.10.2. And then it is compatible with Elasticsearch, wire compatible with Elasticsearch 7.10.2. So if you have an Elasticsearch environment, then you can migrate that to OpenSearch, and then you can expect it to be wire compatible. And then you have the OpenSearch dashboard, which is the Kibana equivalent, which again is derived based on Kibana OSS 7.10.2. And then you have a list of clients, the language clients such as Python, Java, and you also have tools such as Logstash, Beats, that those that have been developed for 7.10.2 OSS version would continue to work with OpenSearch as well. But as I said earlier, there are some folks available for OpenSearch as well. And if you're running Elasticsearch, then there are several different upgrade paths to get into OpenSearch. So if you're on Elasticsearch 7.10, then it becomes an easier upgrade process. So you can do a rolling upgrade or a restart upgrade. But if you're running older versions of Elasticsearch, then you might be able to make use of some of these upgrades, or you can reindex your data, which is more like copying your data from Elasticsearch to OpenSearch. And that could be one way to move away from Elasticsearch and move into OpenSearch. So let's look at some of the common use cases of OpenSearch. Log analysis. So one of the primary use cases for OpenSearch is log and metrics analysis. The logs could be coming from your applications, your host systems, containers, etc. And it's not uncommon to have billions of log lines being generated every day. So when you have such a high volume, how do you make sense of such high volume data? So if you look at logs, they are semi-structured machine data. And OpenSearch can handle that quite well because it is a schema-less document store. And with the logs ingested into OpenSearch, you can look for patterns in your logs. You can normalize your logs. You can also correlate different logs to identify a certain issue as to where it might be coming from. And you can also filter the logs based on several different criteria. That way you can narrow down your search. OpenSearch can also work as a good document store, where you can store different sets of documents. It could be text documents, or it could be other data. And once you have the data in OpenSearch, you can use one of its rich search capabilities, such as autocorrection, autocompletion, and search as you type. And you can there is synonym search as well. And on the analytics front, once you have your metrics in OpenSearch, then you can do some historical data analysis so that you can analyze the trends, and then you can also do forecasting. And a lot of companies use OpenSearch for e-commerce as well. And once you have set up a product catalog in OpenSearch with all your product information, then it becomes much easier to search that data, because OpenSearch comes with capabilities for auto-completion and auto-correction, fuzzy search, and all that. This provides a good user experience when someone is looking for a product in your product catalog. And then some more use cases that we should talk about would be the monitoring. So once you have logs and metrics in your OpenSearch environment, then these metrics could be coming from your network's host or sensors. And then once you have the data in OpenSearch, you can then set up thresholds. And then once these thresholds are breached, you will get notified through alerts. And on the security space, OpenSearch can be quite handy for doing threat analysis. For example, you can monitor your systems for repeated login attempts and things like that. And also for integrity monitoring, doing anomaly detection, and for compliance purposes. In the application performance monitoring field, OpenSearch can be used for real-time performance monitoring, looking at the latency and load of your applications, and then detecting failures in your applications, and then getting alerts based on those can be quite handy. And a lot of data nowadays is time series. These could be metrics, logs, it could be events, or even purchase orders. And OpenSearch is quite capable of handling such data very well, because it has built-in capabilities for machine learning and anomaly detection, which you can make use of to analyze the data. So let's briefly touch upon Apache Lucene. Lucene is an open source high performance search library built with Java. It has been around for many years, and it is a very mature library. And it's used by some of the other popular search engines as well, such as Solr and Elasticsearch. The heart of Lucene is the inverted index, search index. That's how it achieves the incredibly fast search response. So the inverted search index provides a mapping of terms to documents that contains those terms. On Lucene, not only supports searching information such as text, but also numbers and other field types. And it also has a rich search interface with support for natural language searches, wildcard searches, fuzzy searches, and proximity searches. And here is an example of an inverted index. On the left, we have a sample of 3 documents. And on the right, you have the inverted index for these documents. It's showing the mapping from the terms to the documents, and also showing how frequently these terms appear in those documents. And again, this is a simplified version of the inverted index. And an actual inverted index will have a lot more fields, such as the offsets for these terms. So let's look at how OpenSearch makes use of Apache Lucene and clustering to achieve high performance scalable search platform. So Lucene is a search library, but it is not a scalable search engine. So that's where you need something beyond Lucene to provide a scalable solution. So OpenSearch uses Lucene for search, but has additional capabilities that make it a full-featured search and analytics engine. An OpenSearch cluster is a distributed collection of nodes that each perform one or more cluster operations. The cluster is horizontally scalable, so adding new nodes allow the cluster capacity to increase, while your performance would remain pretty much similar. Having a cluster also helps with the data replication. So you can replicate your data across nodes. And then if there's a node failure, you should be able to handle that with no data loss or downtime. And then the nodes in the cluster can be differentiated based on the specific functions that they perform, although any node can perform any cluster operation. And here is a typical OpenSearch cluster with the master nodes, master eligible nodes, the data nodes, and the client nodes. And we will briefly look at the functionality for these different node types. So the master nodes are responsible for maintaining the health and state of the cluster. They coordinate creating, deleting the indices and shards. And they come from a group of master eligible nodes, which are the candidate master nodes. At any one time, you can have only one master node. And so you would need an odd number of nodes for tie breaking purposes. So the data nodes do the actual work. They hold the data and handle requests for ingesting data, requests for searching, and also doing aggregations. So because of that, they are CPU and memory intensive, and typically they tend to be high resource intensive instances. The client nodes are optional, but they help in handling the user request and then trying to load balance them across the different data nodes. Without the client nodes, the request will directly go to one of the data nodes, which then would have to perform the client node functionality to um, send that request out to the other data nodes to complete that request. Having the client nodes help move that functionality out of the data nodes. And let's look at how data is organized within OpenSearch. And here is a high-level overview of how the data would be logically partitioned within OpenSearch. So at the top level, you have the index, which is a logical collection of all your documents. And the index themselves are broken down into what are called as shards. The shards, they themselves map into the underlying Lucene index. And each Lucene index is stored as a collection of segments. These segments are actual files on the file system. So an index is a basic unit by which end users manage the data in OpenSearch. It is similar to a collection of it's similar to a collection in a NoSQL database. And indices contain one or more documents, and they can be many different types. It could be a paragraph from a book, it could be a log line, it could be a tweet, or with the data for a city. So an index can handle several different types of documents. And when you create an index, you typically group similar documents into the same index. They don't need to have the same set of fields in each document, but you try to group them together based on their content. And as we talked about earlier, the indices are internally broken down into shards, and these shards are mapped to the underlying Lucene indices. And then if you look at the documents, they are JSON structures that hold a collection of fields and their values. The fields are key value pairs that make up a document. They can be of several different types, such as numbers, text, keywords, geopoints, etc. Typically, documents in index can have similar content, but not necessarily the same content. So here's an example of a people index, which has information about people in a company, and as you can see, not all of the documents have all the fields. And then at the next level of document organization would be the shards. And an index is broken up into one or more units called shards. And each shard maps to an underlying Lucene index. And the number of shards per index is configurable. So you can have different indices with different number of shards. And the number of shards can have a major implication on the performance of your cluster. So when you do a search, those are performed at the shard level, which means that having multiple shards can help with increasing the search speed. But there is also a price in having too many shards. So if you increase the number of shards, that also increases the cluster state information, which means that the cluster has to maintain a lot more state data, and that would be resource intensive. So a trade-off is to keep shard size between 30 to 50 GB, no matter how large your index is. Even if it is an index can even be a terabyte, but you would break that down into many shards so that they end up between 30 and 50 GB. And when we talk about shards, there are two different types of shards, primary and replica shards. The primary shards are the one that hold the actual data. But then if you would like some redundancy and prevent data loss, then what you could do is you can allow OpenSearch to configure replicas. So once you configure replicas, the replica shards would be created. And OpenSearch tries to allocate these replica shards to nodes other than the ones where the primary shards reside. So with that, if the primary node were to go down, then you would still have access to that data through the replica shards. And the number of replicas, it's an index level setting, and it can be changed at any time. So typically you have one replica, but if you care a lot about your data, then you can configure multiple replicas, and then you can put those replicas not only in the same availability zone, you can also put them across different availability zones so that you have better redundancy there. The replicas shards are not free. They come with a price. Creating replicas means that storing additional data, and which means additional storage space. And they can also slow down your indexing speed, because when you index data, it needs to be written to both the primary and replica shards. And let's look at how indexing works in OpenSearch. Any input data to OpenSearch is analyzed and tokenized before it gets stored. The original document is available as is in OpenSearch in a special field called _source. So the analyzers and normalizers take the input data, convert them into a sequence of tokens or terms, which then get stored in the Lucene inverted index. OpenSearch has pre-built analyzers and normalizers that you can make use of, or you can build your own custom analyzers and normalizers. If you look at the pre-built analyzers, an example would be the standard analyzer, which breaks text into grammar-based tokens. And another example would be the white space analyzer, which takes text and breaks them down based on the white space. The white space analyzer could be handy when you're trying to deal with the logs, because logs doesn't make sense to be broken down based on grammar. And looking at analyzers, it is a combination of character filters, tokenizers, and token filters. And then along with the pre-built analyzers, you can also build custom analyzers by selecting a combination of character filters, tokenizers, and token filters. And if you look at the flow of data through an analyzer, the input data goes through the character filters, one or more of them, and then output of that, it is fed into a tokenizer. You have only one tokenizer, and then that converts that input data stream into a list of tokens. And then they pass through a set of token filters, which can add, remove, or modify the tokens. So taking a closer look at the token character filters, they pre-process the input text before forwarding it to the tokenizer. So they work by adding or removing or even changing characters in the input text. An example would be the built-in HTML character filter that strips HTML elements and also decodes the HTML entities before it gets sent to the tokenizer. You can also chain one or more character filters, and then they will be applied in the order in which they are specified. And then looking at the tokenizers, they convert the input stream of characters into tokens based on the certain criteria. But for example, the standard tokenizer that goes along with the standard analyzer breaks text into tokens based on word boundaries. And then it also removes any punctuations. On the other hand, the white space tokenizer breaks text just based on the white space. And the token filters post-process the tokens from the tokenizer. The token filters can add, remove, or modify the tokens. If you look at the example of the ASCII token filter, which is a pre-built token filter, it will convert the Unicode characters into their closest ASCII equivalent. And another example would be the stemming token filter, which converts words to their root form before they get stored. And in terms of indexing, when you index the data, they can be stored in several different field types. Some of the field types, common field types, are text, keyword, numbers, and the geopoint. So the text type, it's primarily used to index human-generated text data, which could be tweets, social media posts, or it could be the contents of a book or product descriptions. They are quite useful for performing phrase queries, fuzzy queries, etc., which is like a closest match query. On the other hand, the keyword type are used for structured content such as names, IDs, ISBN numbers, etc. And they are handy for sorting, for doing aggregations, and also for running scripts, as they are stored in a columnar format, and which makes them quite fast. The numeric data types are used for storing numbers such as integers, floats. So when you choose a numeric type, you want to choose the one that's the smallest type that can handle the input range to conserve storage space. Internally, they are stored as BKD trees. And the other quite useful field type would be the geopoint type. It is used to represent location information such as latitude and longitude. So you can, with that information in your documents, then you can use queries that rely on location and distance. And this is quite handy when you're doing searches based on maps. So if you want to restrict your search to a certain geographical area, then this, you would make use of the geopoint type. And again, they are used, they are internally stored as BKD fields. So once you have the documents indexed, then OpenSearch lets you search for those documents using several different mechanisms. And OpenSearch uses a distributed search algorithm to match the documents against the user input. The searches can be exact match, such as the keyword searches, or relevancy based, such as the text searches. If you look at OpenSearch, it focuses more on search speed than accuracy. But in a lot of cases, you can control the level of accuracy that you need. So that way you can have a trade-off between speed and accuracy. And OpenSearch also provides a near real-time search, which means that all documents will be available for search except for the ones that are most recently indexed. Those documents have to be refreshed before they become available for a search. So that's why it is considered as a near real-time search engine. And OpenSearch uses two different phases when you do a search, one being the query phase, and then the next would be the fetch phase. During the query phase, the input request is sent to all the shards associated with that index. These shards can be primary or replica because the replicas have the same exact data as the primary. And then the shards themselves will run the search locally and then send those results back to the node that initiated the search request. The results don't contain the actual document, but only contain metadata such as document IDs and scores. And during the fetch phase, the node that received the search request, which is the coordinating node, would gather all the results, intermediate results from the query phase, and then form a final list of final set of results, and then it would use the fetch phase to get the actual documents from the shards, and then return those results back to the user. And when it comes to document searching, OpenSearch uses a scoring algorithm, and this is useful for doing searches across text fields. And the default scoring algorithm is BM25, which is an improvement over the TF-IDF algorithm widely used in natural language processing. In particular, the BM25 takes into account the field length and applies term frequency saturation. In its simplest form, the score would be calculated based on the term frequency, the inverse document frequency, and the norm. The term frequency indicates how frequently a given term appears in the field. So if a term appears more than the other term, then it is considered to be more significant. And on the other hand, the IDF tells us how frequently the term appears across all documents in the index. If it appears more commonly, then the term is considered to be less relevant. This is how you can provide less relevant to common words when you do the search. And on the other hand, the norm takes into account the length of the term. For the same term frequency, a shorter field is considered to be much more relevant than a longer field. And in certain circumstances, like when you're searching for logs, the norms don't help with the search results, so you can disable them. And let's briefly look at aggregations and how they help with analyzing the data and doing visualizations and dashboards with your data. So OpenSearch is not only a search engine, but has built-in advanced analytic capabilities. So with aggregations, you can do filtering, you can do, you can categorize your documents, you can calculate metrics on those documents, and then you can build aggregation pipelines by combining multiple aggregations. There are many different aggregation types which can be used, and then they can be classified as metrics aggregations, bucket aggregations, and pipeline aggregations. And here is an overview of how the aggregations are related. Let's go through them one by one. The bucket aggregations categorize the matching set of documents into buckets based on the bucketing criteria. So the bucket criteria could be based on unique values of a field. Like you can do bucketing based on the product category, as an example, or it could be a date range. So you can do bucketing based on product orders, order dates, and you can also do bucketing on other criteria as well. They can be used to paginate all the buckets. For example, the composite aggregation allows you to do aggregations on your data and then paginate through all those buckets. And they can also be useful for providing faceting. So when you have product search on your website, then when some user searches for a specific product, then you can provide faceting that you typically see on the websites where you have product categories, product by brand and price range and all that. That's all possible through faceting. And the bucket aggregations can also be used to provide input to the metric aggregations. And when talking about metric aggregations, they calculate metrics on the values generated from the documents. These values could be coming from specific fields in the documents being aggregated, or they can be generated dynamically through scripts. And OpenSearch uses a language called Painless, which can be used to write scripts to act upon the documents. And the metric aggregations can also be included as sub-aggregations to bucket aggregations, and they will provide metrics per aggregated bucket. There are two different types of metric aggregations: the numeric aggregations, which provide numeric metrics such as max, min, sum, average values, and also some extended stats. Whereas the non-numeric aggregations provide non-numeric data. An example would be the top hits aggregation, which can be used to produce top matching documents per bucket. And then finally, the pipeline aggregations, they can be used to compute metrics, but they don't act on the documents themselves, but they act on the output of other aggregations. And this makes it possible to build a chain of aggregations. And they can be further classified as parent or as sibling pipeline aggregations. With parent pipeline aggregations, you compute new aggregations based on the output of the parent aggregations. But then with the sibling aggregation, the new aggregations are based on the output from one or more sibling aggregations, which are at the same level. Here is a brief overview of the OpenSearch ecosystem. You have OpenSearch, and then on the left, you have different ways to get data into OpenSearch. And on the right, you have different tools and clients that you can use to interact with OpenSearch. And there are many more tools and clients available, but these are the common ones. And there is a rich set of documentation available on each one of them online. So far we looked at OpenSearch and some of the architectural aspects of OpenSearch. And thanks for attending this presentation, and I hope it was useful to you. If you have any questions or comments, please feel free to reach out to me at my email, sethuraman.muthukaruppan@netapp.com. Thank you.